Okay, so what can go wrong with experiments? The whole thing behind our randomized comparative experiment depends on our ability to treat everything the same in every way except for actual treatments being compared. So there is no difference between the groups. We've controlled every variable except for the treatments themselves. Is that actually what happens in real life? Not really. So we often want to compare a situation involving specific treatment to a status quo. If you've never heard that status quo statement, that's what we would expect to occur without any outside influence. So sometimes we'll say, okay, what is this idea of a status quo versus what does the treatment themselves do? So what we do is we need to establish a baseline. That is our status quo. What do we expect to happen with business as usual? That's what we call our control group. Our control group doesn't have any outside influences. It's just what occurs naturally. In order to avoid bias, we use blinding. Again, my AP Stats kids here are probably going, woohoo, I know this stuff. Blinding is what happens when somebody doesn't know what's going on. And I don't mean doesn't know that, hey, I'm part of an experiment, but rather they don't necessarily know what treatment that they're getting. The classes of individuals that can affect the outcome, these are the people that actually affect the outcomes, your response variable. Either those who actually influence the results, the subjects, those are the people getting the results or getting the treatments, the treatment administrators, those who are distributing the different types of treatments themselves, and the technicians, which would be the people that actually measure the results. So if I'm talking about my AP Statistics example, the students in the class would be the subjects. They can influence the results. The treatment administrators, that would be the teachers, the people that are distributing the treatments. The technicians, those people who are recording the results, whether that's a standardized test or whether that's a teacher or whether that's administration. And the other end of that spectrum is those who evaluate the results. Notice technicians collect results, but they're not evaluating them. The evaluator would be judges, treating physicians, or other such things. People that are trying to decide, well, what was the outcome? Do we see what we were expecting to see? Now, when all individuals in either one of these categories are blinded, in other words, they don't know which treatment they're receiving, or that they are receiving anything other than the status quo, it is a single blind experiment. Now again, single blind means everybody in either this group, the influencers, so those receiving the treatment, those dispersing the treatment, and those measuring the treatment, those people that actually come into contact with the treatment itself, or those who examine and record the results. If instead everybody in both classes is blinded, the experiment is double blind. Now that's actually something that's possible to do. The subjects don't know exactly what treatment they're getting, neither do the people that are administering it, nor do the people that are measuring it. They are simply, for example, if you're doing some sort of a drug trial, the subjects don't know what they receive, the doctors don't know what's in the vials that they're delivering to the patients, and the technicians who are recording blood pressure or temperature or rate of healing don't know what it is. But then again, the people that collect all of those results and look at each individual case separately to determine if it was successful, they don't know who had what either. And the reason why we do that is if we understand what outcomes we want to see, oftentimes judges might say, you know what, that result was what I was looking for, when if in effect it really wasn't. Placebos play a big role in this because the fact that we're doing any kind of a treatment, people might believe, hey, you know what, this is going to have a specific effect. So to separate the effects of treatment of interest, we use controls that mimic the treatment itself. And a lot of times it just mimics it in appearance. A fake treatment that looks just like the treatment being tested is called a placebo. Now, it's the best way to blind subjects from knowing whether or not they're receiving the treatment. Because a lot of times, just thinking you're receiving something that's going to make you do better actually does make you do better. You're thinking, hey, it's the power of positive thought, if you've ever heard of that saying before. Or likewise, some people automatically expect, oh, I'm going to have side effects from this. Oh my gosh, and they get really, really nervous, and then their body actually produces those side effects. This is called a placebo effect. A really cute comic kind of displaying that. Here we have a patient who says, I feel lousy, doc. And the doctor turns around and says, you need to laugh more. Laughter is the best medicine. He says, I must be in the placebo group because you know why that doesn't work for me. And it's kind of a ridiculous thought. You can't tell if you're in a placebo group or not, and even that idea itself is silly. Placebo effect occurs when someone taking the same treatment, not the sham treatment. Oh, I guess it is the sham treatment. Yeah, the treatment that's not actually working resulted in a change in the response variable. So, for example, if I'm telling you this magic drug cures everything and it's actually just sugar water, all of a sudden the person starts feeling better and, oh, my pain has gone away. That's a placebo effect. And it highlights the importance of effective blinding and comparing treatments with a control. Because just that idea of, I think this is going to help, sometimes actually does make it help. Placebo controls are so effective that you should use them whenever possible. If you can do single blind, oh my gosh, do single blind. If you can do double blind, doubly better. The more, the better when it comes to blinding and placebos. So the 4 principles of experimental design, I have a feeling this would probably be, of all the questions, one of the best questions for me to ask you. The 4 principles is control. Without control, why have an experiment? Just do an observational study. We can control sources of variation other than the factors we are testing by making conditions as similar as possible for all treatment groups. When you control, you help to eliminate confounding variables. Well, this is a randomized design here, so maybe randomization would work. Randomization allows us to equalize the effects of unknown or uncontrollable sources of variation. So all of this is about control. Randomization helps us level out some of the effects of those uncontrollable sources. It doesn't eliminate those effects, but because we have such a variety of treatment levels and a variety of subjects, we can usually see past them. But without this randomization, we don't have a valid experiment, period, because we will not be able to use statistics to draw conclusions. There are too many confounding variables. We can't get past it. You can't establish an association, not even get close to a cause and effect. So control and randomization. Control and more control. And more control. We want to be able to replicate. Replication means that you're repeating the experiment, not necessarily to the same subjects all the time, but to a different number of subjects. Just one subject, that's called an anecdote. It's just a story. It's just, oh, look what happened. But if we do it over and over again to more and more people, a larger and a larger pool, we start to have better and clearer results. But when the experimental group is not representative of a sample of the population, we want to make sure that we replicate the experiment for different groups, different situations. Control, control, control. Replication of an entire experiment at different levels is essential in the science of statistics. And last but not least, block. Block is something we haven't mentioned yet. When we have attributes in our units that we are not studying and we can't control, be it gender or age or current health levels or past experiences, those affect the outcomes of an experiment, but we can't control someone's age. If we group similar individuals together and then randomize within each of those blocks of groups, we can remove as much variability due to the difference among the blocks as possible. Blocking is important. It's kind of a compromise between randomization and control, but it's not necessarily required to be a good experiment. Okay, so our best experiments then are randomized. They're randomized in the assigning of groups. They're randomized in the assigning of treatments. They're comparative, because that is the whole purpose of an experiment, is to compare our outcomes to determine cause and effect. A perfect experiment is double-blinded, where neither those who are actually coming in contact with the treatment nor those who are judging the outcomes know what was done, and they are controlled by a placebo to eliminate the I think I feel better, therefore I feel better, or I think I'm getting the treatment, therefore I feel better experience. And blocking is another aspect, although not always used, is usually a good group, because when groups of units are similar, we can gather them into blocks. Again, and this is taking a little bit of the randomization out of it, but we're still randomly assigning students to these blocks, or we're assigning treatments to the blocks. Because blocking isolates variability. Remember, variability is the amount of difference, the amount of change within a group. And this is the differences between the blocks themselves, so we can see the differences due to the treatments more clearly. Maybe I'll take a group of AP Statistics students who come from functions trig, and I want to look at that. Or I want to look at the students who come from Calculus AB, Calculus BC, Algebra 2, or some other method. Because blocking them by that, it reduces the variability of their past math experience. Or if I'm talking about people who are trying to lose weight, I want to block them based off of their actual weight, based off of their activity level, based off of their gender, or any health issues that they might experience. When randomization occurs only within the blocks, that's a randomized block design. So that means we have our two different groups, but then the blocks themselves are randomized. So my blocks are girls and boys. Then I randomly pick girls and I randomly pick boys. That's a randomized block design. We form our blocks based on the most important and unavoidable sources of variability, our lurking variables, what we believe to have some sort of an association, but we can't necessarily control among our experimental units. This allows us to average out the effects of the remaining lurking variables and hopefully create an unbiased comparison of the treatments. So we can't say, well, somebody with a lot more weight to lose is going to lose it a little bit quicker than somebody who's closer to their goal. So we want to be able to eliminate those differences and control what we're comparing so that we have an accurate picture of what's going on. Blocking is the same idea for experiments as stratifying is for sampling. This is extremely important to understand. Blocking is to experiments as stratifying is to sampling. Both methods groups together students that are similar or subjects that are similar and randomize within those groups as a way to remove unwanted variability. Remember when we were doing stratifying, it was saying, okay, we have freshmen, sophomores, juniors, and seniors. Okay, I can look at the freshmen and get a random selection of them, same with the sophomores, the juniors, and seniors, so that I get a slice of every single layer of that cake. We use blocks to reduce variability so that we can see the effects of the factors. We're not interested in the effects of the blocks themselves. We don't really care about the effects of being a freshman, a sophomore, a junior, a senior. But we're just trying to eliminate some of those lurking variables. Does age play a role? Does experience play a role? So the big saying is, control what you can, block what you can't control, and randomize to create comparative groups. Let me repeat that for you. Control what you can, block what you can't control, and randomize to create comparable groups. Hugely important to understand. Because experiments are about control, but you can't control everything. So when you can't control something, we block it, and then we randomize within those blocks so that we can compare. Okay? Here's an example of this. Remember before I gave you a picture of a design, and I said there are certain things that you absolutely have to state. You have to state who your units are. What are you looking at? You have to state whether or not your groups or how your groups are dealt with. We might have two different groups. Block A, which has 12 tomato plants. Block B, which has 6 tomato plants. Now those numbers probably have more to do with what type of treatments they're going to go with or what the size of the population originally began with. Maybe block A is our typical tomato plants and block B are our organic tomato plants. And then within that, notice here we said we blocked it. You must state that blocking. You must tell that these groups are formed by blocking. You must state that to go from the blocks to our groups, we have random assignment. If you leave that out, I could just assume that you just said, all right, first 2 people, group 1, second 2 people, group 2, third 2 people, group 3. You've got to be clear that this is actually random assignment. And then from those groups, we receive different treatments. One group receives the control treatment, probably just water with nothing in it. Second group receives the second treatment, maybe water with a half a dose of fertilizer. And group 3 receives the third treatment, the full dose. And then we are going to compare the results within one block, and we're going to compare the results within the other block. But we don't necessarily compare between the 2 blocks because we're looking for the effects of the treatments, not the effects of regular versus organic. Okay, blocking allows us to eliminate those lurking variables. Now, matched pairs design is something that's going to come back again and again and again, especially later on in the year when we start talking about actually running tests. We do a matched pairs design when we have similar experimental units. This is a way to match subjects to reduce variability. It's a lot similar to blocking, but it has slightly different outcome. Matched pairs, each block consists of a pair of matching things. You can think of them as twins, or you can think about them as siblings, or a husband and wife category, or one person who's receiving 2 different treatments. Chances determine which unit in each pair gets each treatment. Sometimes your pair is a single unit that receives both treatments. For example, a pair might be a batter who hits once left-handed and hits another times right-handed. Or a pair might be one student to see how attentive they are at 8 o'clock in the morning versus 2 o'clock in the afternoon. So they're receiving both treatments. Since the order of the treatment can influence the response, chance is then determined to decide what treatment is applied first for each unit. That's randomized. Now we're looking at a lot of stuff that can go wrong here. If you can't run a perfect experiment, you can't control the treatments themselves, you can't blind the groups, you can't randomize your assignment, don't run away from it. If you can't perform an experiment, an observational study can be still a good choice. It's a starting point. But always be careful of confounding variables. Randomization helps us to ensure that the factors that we see are not confounded with your treatment levels, because remember, it tries to spread out the effects of confounding variables. But understand that confounding can't be avoided all the time. And so when it can't, you have to report that along with your results. You know what? Bad things happen even to the best of experiments. So we do that by recording every little piece of information that can occur. You know what? If I wanted to do a study on the effects of a flipped classroom, and then in the middle of the year, it's horrible, there's snow, school is canceled left and right, we can't get through a full week of class without an interruption. Hey, you know what? I can't always control that. So we just have to make sure that we always record whenever something like that occurs. Make sure you're very clear, complete, concise, and in context. And while this might not affect you right now, when you're out in the real world, The big thing is don't spend your entire budget on the first run. We always do a small pilot before running a full-scale experiment, because if the small pilot blows up in your face or you realize that there are significant issues, you haven't blown your whole budget. You will learn things that help you make the full-scale experiment even better. It allows you to tweak, it allows you to grow. But if you don't have something to fall back on to make that second experiment possible, remember that idea of replication, if you can't repeat it because you have no money, what's the point? So we've covered a lot of stuff today, and I appreciate you guys hanging with me through it all. Please, please, please be prepared for class. If you need to go back and view a couple of these sections again, do so. Make sure you understand the main components behind a successful experiment. Make sure you understand the different types of blocking that occur, what's expected in your designs, and I hope we can actually get a lot of really good discussion in class. Thanks for your patience, thanks for your attention, and see you next time.